Welcome to section 1.3. So our introduction to many of these different ideas of matrices and so forth is going to continue as we talk now about equations using matrices and vectors. So let's talk about what are vectors and what are their different properties. So a vector is a matrix with only one column. Okay, I'm half lying on this because that's not the technical definition in chapter 4. We'll actually get to technically what is a vector. But for the sake of this right now, as many people think of it, a vector is a matrix with only one column. Be careful, don't ask a physicist. They'll tell you a vector is a direction with magnitude, which it works for 3D, but it doesn't work for nth degree. So a common example of a vector would be something that looks like this. Now, we can write it as this nice vertical one. There's some other notation we also can use. But notice that we write a V with an arrow over it. We also can use a U and so forth. So we always, now we usually do a bold-faced, writing it by hand, that stinks. But in the actual class, you'll notice vectors always have that arrow notation over the top of them. My math lab really is big on this. So what are the properties of vectors? Well, first off, two vectors are equal if and only if the corresponding components are equal. It should make sense. So you just hold them up next to each other and everything matches up perfectly, we're good. If I take two vectors and they're both in Rn, then their sum is I just add them component-wise. So I add the first ones together, the second one together, and so forth. Third, a scalar multiple written CV means I literally multiply each component by that scalar. All right, so let's just do some examples of these properties to get you going on it. So here's my vector U and my vector V. So U plus V is literally I'm going to add each component. So I'm going to add 1 plus 2. I'm going to add -2 and -5 and 3 and -4. Go ahead and add those together and find the new vector. All right, we should just come up with 3, -7, -1. Now again, we're not going to do crazy things for the sake of this class, but these properties extend and allow us to do really crazy things in areas. Now, what if I do 4V? So I'm going to take the vector V. I even wrote it down for you down here below. And this 4 means that 4 is going to multiply to every single term. So what is my new vector? Well, hopefully you're thinking that's 8, -20, -16. Boom. All right. So we can scale them. We can add them. Same lines, by the way. That means we can also subtract them. Subtraction is just like adding a negative version. So that's cool. So other properties, if I have 3 vectors, notice they all have to be of the same dimension. Then if I have 2 of them, I can add them in any order, just like regular numbers. Okay. If I have 3 of them added, I can add any 2 together and then add the third one, just like regular numbers. If I add the 0 vector, it doesn't change anything because any number plus 0, okay, that's obvious. If I add a vector plus the negative version of the vector, it gets me a 0 vector. Okay, again, this feels just like regular numbers. C times UV is, we can distribute C plus D times V, boom, okay, this is cool. Everything's looking just like regular numbers. 1 scale, okay. So hopefully you're like, I got this, this is making sense. But now let's talk about understanding them geometrically, because vectors do have some geometric sense. Now this is only going to really make sense in 2 dimensions. So here are 2 vectors that my scale got completely wonkified. All right, so 1 second. All right, so since my visual slides were not quite working, I am employing instead a different software program. I apologize for that. It's easier than me trying to fix my slides. So here is something called GeoGebra. So if all of you have graphing calculators, This actually does all this stuff in your graphing calculator, and it's super cool. It doesn't cost you, it's actually completely free. So GeoGebra, notice I typed in vector u, which is 1, 2. Then if I do vector and I do the 0.31, gives me my vectors just like I actually wanted. This is the vector u, and this is the vector v. However, now comes the question of what is u plus v. And notice that gives me a whole new vector. Well, the reason for that is if I took this vector u and I got myself off. So if I just do a new vector where I'm going to do this with a starting point of 2, 1, and then end point of 4, 3. Oh, I want 1, 2, and you can see that my new vector, vector A, is if I took vector V and just split it up here. So because of this, we get this nice kind of what's also known as a parallelogram kind of idea, where if I did U first and then I did V, use a little spot, right? So if I did V first and then I took vector U and essentially put its tail right here and then its head and its tail where it shot to, up here, it will all come to the same point. So really, u plus v is going to be this vector along here. Notice also, if I just did the vector, let's say 2u, that's my new vector b. It's twice as long. So it goes u, and then it goes u again. So this is the idea of what they mean. And again, I'm doing this in 2 dimensions, but these ideas expand into infinite dimensions. And so we can actually utilize these to look at things over and over and over again beyond how they add up. And this gives us an idea of linear combinations. So come back in the next video, I will explain what these linear combinations are definitively and go through more examples.